In electrical systems, understanding grounding requirements for separately derived sources is crucial for safety and code compliance. A separately derived source is an electrical power source, such as a generator, transformer, or solar inverter, that is electrically isolated from the main power supply system. The National Electrical Code, or NEC, provides specific guidelines for grounding these sources to ensure proper operation and protection against electrical shock. In the described scenario, a 120 volts 40 amps breaker feeds a single-phase 120 to 600 volts 5 kVA step-up transformer. The 600-volt circuit runs 1300 feet underground using number 4 XHHW conductors to a matching transformer, with the 600 volts is stepped down back to 120 volts for utilization. The question revolves around whether grounding is required, optional, or prohibited for the 600-volt separately derived source. According to the NEC, specifically Section 250.20, grounding requirements differ based on the voltage level and the type of system. For a new 120 volts feed from the second transformer, grounding one leg is indeed required. This is because the 120 volts system is a low voltage system supplying premises wiring and is therefore subject to specific grounding requirements outlined in NEC Section 250.20. However, the NEC does not explicitly mandate grounding one leg of the 600 volt separately derived source in this particular configuration. The key consideration is that the 600 volt circuit is an intermediate voltage level between two transformers. The NEC grounding requirements for separately derived sources primarily focus on the output side of the transformer that supplies premises wiring. Since the 600 volt circuit does not directly supply premises wiring, but rather feeds another transformer, the grounding requirements are different. Grounding the 600 volt circuit is optional. This means that there is no explicit requirement in the NEC to ground one leg of the 600 volt separately derived source. However, there may be situations where grounding the 600 volt circuit could be beneficial or even necessary for specific operational or safety reasons. For instance, grounding the 600 volt circuit might be desirable to provide a more stable reference point for voltage measurements or to reduce the risk of voltage transients. It is important to consult with a qualified electrical engineer or inspector to determine whether grounding the 600 volt circuit is appropriate for the specific application. Grounding is not prohibited. The NEC does not prohibit grounding the 600 volt circuit. In fact, there may be situations where grounding the 600 volt circuit is recommended or even required by local codes or regulations. The decision to ground the 600 volt circuit should be based on a thorough evaluation of the specific application and a careful consideration of the potential benefits and risks. It is essential to ensure that any grounding practices comply with all applicable codes and standards. Several factors influence the decision to ground or not to ground the 600 volt circuit. Firstly, the type of system grounding is an important consideration. There are several types of system grounding, including solid grounding, impedance grounding, and unrounded systems. Each type of system grounding has its own advantages and disadvantages, and the appropriate choice depends on the specific application. Secondly, the presence of sensitive electronic equipment is a factor. If the 600 volt circuit supplies sensitive electronic equipment, grounding may be necessary to protect the equipment from voltage transients and other electrical disturbances. Thirdly, the length of the circuit is a factor. In long circuits, such as the 1300 feet underground run in the scenario, grounding may be desirable to reduce the risk of voltage drop and improve voltage regulation. Finally, local codes and regulations may dictate grounding requirements for specific types of installations. In summary, while NEC Section 250.20 requires grounding one leg of the new 120 volts feed from the second transformer, it does not mandate grounding one leg of the 600 volts separately derived source. Grounding the 600 volt circuit is optional, not prohibited, and should be evaluated based on the specific application, the type of system grounding, the presence of sensitive electronic equipment, the length of the circuit, and local codes and regulations. To further elaborate on the NEC sections that are relevant to this scenario, we can look at Article 250, which provides the general requirements for grounding and bonding. Section 250.20 specifically addresses systems that are required to be grounded. This section lists several conditions under which AC systems must be grounded, including when the system can be grounded so that the maximum voltage to ground in the ungrounded conductors does not exceed 150 volts. This is the reason why the 120-volt system on the output side of the second transformer must be grounded. Now, let's consider the step-up and step-down transformers in this setup. The step-up transformer takes the 120-volt supply and increases it to 600 volts for transmission over a long distance. The step-down transformer then reduces the 600 volts back to 120 volts for utilization. Each of these transformers creates a separately derived system. The NEC defines a separately derived system as an electrical source that is electrically isolated from the primary power source. This isolation is typically achieved through the use of a transformer or generator. When dealing with separately derived systems, it's essential to understand how to properly ground and bond them to ensure electrical safety and proper system operation. The grounding requirements for separately derived systems are outlined in NEC sections 250.30 and 250.32. These sections provide detailed instructions on how to establish a grounding electrode system for separately derived systems and how to connect the system to ground. In the case of the 600-volt system, since it does not directly supply premises wiring, the grounding requirements are less stringent. However, there are still some considerations to keep in mind. Firstly, it's important to ensure that the transformer itself is properly grounded. This typically involves connecting the transformer's metal case to the grounding electrode system. Secondly, it's important to consider the potential for ground faults in the 600-volt system. A ground fault occurs when an ungrounded conductor comes into contact with a grounded surface. If a ground fault occurs in an ungrounded system, it can create a dangerous situation, as there is no low impedance path for fault current to flow back to the source. This can result in high voltage on the grounded surfaces and an increased risk of electrical shock. To mitigate the risk of ground faults, it may be desirable to ground one leg of the 600-volt system. This would provide a low impedance path for fault current to flow back to the source, which would help to quickly clear the fault and prevent a dangerous situation. However, grounding the 600-volt system can also have some drawbacks. One potential drawback is that it can increase the risk of circulating currents. Circulating currents are unwanted currents that flow through the grounding system. These currents can cause heating and energy losses, and they can also interfere with the operation of sensitive electronic equipment. Another potential drawback of grounding the 600-volt system is that it can make it more difficult to troubleshoot ground faults. In an ungrounded system, a single ground fault will not typically cause a disruption in service. However, in a grounded system, a single ground fault will typically cause the overcurrent protection device to trip, which can interrupt service. This can make it more difficult to locate the source of the ground fault. Ultimately, the decision of whether or not to ground the 600-volt system is a complex one that depends on a variety of factors. There is no one-size-fits-all answer, and it's important to carefully consider the potential benefits and drawbacks of each approach before making a decision. It's also important to consult with a qualified electrical engineer or inspector to ensure that the grounding system complies with all applicable codes and standards. In addition to the grounding requirements, it's also important to consider the bonding requirements for separately derived systems. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault current to flow back to the source. This helps to ensure that all metal parts of the electrical system are at the same potential, which reduces the risk of electrical shock. The bonding requirements for separately derived systems are outlined in NEC section 250.30. This section provides detailed instructions on how to bond the system to the grounding electrode system and how to bond all metal parts of the system together. In the case of the 600-volt system, it's important to ensure that the transformer case, conduit, and other metal parts of the system are properly bonded together. This will help to prevent dangerous voltage differences from developing between these parts and reduce the risk of electrical shock. In summary, when working with separately derived systems, it's essential to understand the grounding and bonding requirements outlined in the NEC. These requirements are designed to ensure electrical safety and proper system operation. The decision of whether or not to ground the 600-volt system is a complex one that depends on a variety of factors. There is no one-size-fits-all answer, and it's important to carefully consider the potential benefits and drawbacks of each approach before making a decision. It's also important to consult with a qualified electrical engineer or inspector to ensure that the grounding system complies with all applicable codes and standards. Let's now delve deeper into the specifics of XHHW conductors and their suitability for underground installations. XHHW stands for cross-linked polyethylene high heat resistant, water resistant. It's a type of insulated electrical wire commonly used in power distribution and control circuits. The XHHW insulation is made of a cross-linked polyethylene material, which provides excellent resistance to heat, moisture, and abrasion. This makes XHHW conductors well suited for both wet and dry locations, as well as for direct burial applications. When used for underground installations, XHHW conductors must be installed in accordance with NEC Article 310, which covers conductors for general wiring. Specifically, Section 310.15 provides guidance on ampacity, which is the current carrying capacity of a conductor. The ampacity of a conductor depends on several factors, including the conductor size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. When installing XHHW conductors underground, it's important to consider the soil conditions and the depth of burial. The NEC specifies minimum burial depths for different types of wiring methods in Table 300.5. These burial depths are designed to protect the conductors from physical damage and to ensure that they operate within their rated temperature limits. In this scenario, the number 4 XHHW conductors are used for the 600-volt circuit, which runs 1300 feet underground. It's important to ensure that the conductors are properly sized to handle the current load and that they are installed at the correct burial depth. Additionally, it's important to consider the potential for voltage drop over the long distance. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can even damage the conductors. To minimize voltage drop, it's important to use conductors that are large enough to handle the current load and to keep the circuit length as short as possible. The NEC provides guidance on voltage drop in informational note number 2 to section 210.19a on, which recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. When calculating voltage drop, it's important to consider the conductor size, the conductor length, the current load, and the conductor's impedance. There are several online voltage drop calculators that can help with this calculation. In addition to voltage drop, it's also important to consider the potential for inductive reactance in long AC circuits. Inductive reactance is the opposition to the flow of alternating current caused by the inductance of the conductors. Inductive reactance can cause voltage drop and can also reduce the power factor of the circuit. To minimize inductive reactance, it's important to use conductors that are closely spaced and to avoid long parallel runs of conductors. In summary, when installing XHHW conductors underground, it's important to follow the NEC guidelines for ampacity, burial depth, voltage drop, and inductive reactance. These guidelines are designed to ensure that the conductors operate safely and reliably. Let's explore the concept of kVA, which stands for kilovolt amperes, is a unit of apparent power in an electrical circuit. Apparent power is the total power that is being supplied to the circuit, regardless of whether it is being used to do work. It is calculated by multiplying the voltage by the current. In contrast to apparent power, real power is the actual power that is being used to do work in the circuit. It is calculated by multiplying the voltage by the current and the power factor. The power factor is a measure of how effectively the apparent power is being used to do work. A power factor of 1 indicates that all of the apparent power is being used to do work, while a power factor of 0 indicates that none of the apparent power is being used to do work. In this scenario, the step-up transformer has a rating of 5 kVA. This means that the transformer can supply up to 5 kVA of apparent power to the 600-volt circuit. However, the actual power that is being delivered to the load will depend on the power factor of the circuit. For example, if the power factor is 0.8, then the real power being delivered to the load will be 5 kVA multiplied by 0.8, which equals 4 kilowatts. When selecting a transformer for a particular application, it's important to choose one that has a kVA rating that is sufficient to handle the load. It's also important to consider the power factor of the load when determining the required kVA rating. If the power factor is low, then a larger transformer will be required to deliver the same amount of real power. In addition to kVA rating, transformers also have voltage and current ratings. The voltage rating indicates the maximum voltage that the transformer can handle, while the current rating indicates the maximum current that the transformer can handle. It's important to choose a transformer that has voltage and current ratings that are appropriate for the application. Transformers are essential components of electrical power systems. They are used to step up or step down voltage levels to match the requirements of different equipment and loads. By understanding the kVA, voltage, and current ratings of transformers, it's possible to select the right transformer for a particular application and ensure that the electrical system operates safely and efficiently.